Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to talk about the final list of applications of differentiation, and it's all about something called differentials. And we have four course learning objectives to achieve today. The first one is a very important one, in fact. It's about understanding the concept of a tangent line approximation, and this allows us to approximate really complicated functions by using linear functions. So that allows us to make estimation about those functions locally. And the second one is about comparing the value of the differential dy with the actual change of the function values. It's called delta y. And this concept is going to allow us to estimate a propagated error using the differential concept. And finally, we're going to find the differentials of functions using differentiation formulas. All right, we have a long list of learning objectives. What I'm going to do here is that I'm going to sort of like merge the fourth learning objective into the second learning objective so that we have only 3 videos in a row. Let's get started. All right, let's start with the tangent line or linear approximations of functions. So to have an approximation, we have to have a differentiable function at the point C. So the point is very important. In fact, C and f of C is where the approximation is going to happen. So what we're going to do is essentially to write down the equation of the tangent line at this point. And this is something that we have been doing all the time. So all we need is the derivative of the function evaluated at C. That's in fact the slope of the tangent line, and we write down the point slope form of the tangent line. And if you solve this for y, so you get the expression or equation of the tangent line. So we call it tangent line, but right now we're going to use this for the purpose of approximating a function, and this is called the tangent line approximation or linear approximation of f at C. And you can see that C is a constant because C is a point where you have the approximation for. So these guys are all constants. So then you have the graph of a linear function of x. So here the catch is that the graph of the tangent line is very close to the graph of f at point C. Why don't we use the values of y to approximate function values for x's very close to C? In other words, as x approaches C, then the limit of y is f of C. So for that reason, around C, we can talk about good approximations of function values by the tangent line approximations. All right, let's apply this concept to the function 1 plus sine x at the point 0 and 1. So in other words, C is equal to 0. So we're going to use a table in one row. We're going to have the values of the linear approximation or linear function in the neighborhood of C equals 0. And in the next row, we're going to have the function values and see how far we are from the actual values by using the tangent line approximation. And here is the tangent line to the graph at the point 0 and 1. This is the point slope form of the tangent line. And all we're going to do is to calculate f prime at 0. So we have f of x to be 1 plus sine x. So f prime of x is cosine x. And f prime evaluated at 0 takes you to cosine at 0, which is equal to 1. So all we're going to do here is to look at f of 0 as well, by the way. F of 0 is in fact 1 plus sine of 0, which is also 1. So this takes us to 1 plus 1 times x minus 0, which is essentially equal to 1 plus x. So 1 plus y equals 1 plus x is a line. So that line is going to be an approximation of the function at 0. All right, here's the table I was referring to. So here we go. We start with c equals 0, and we got sample points around c equals 0. So I picked 0.01 on the right, negative 0.01 on the left, and we were slightly diverging away from the point of approximation. So the next points that we considered would be 0.1 and negative 0.1. And again 0.5 and negative 0.5. You can change those numbers the way you want. And the next thing is function evaluation and a tangent line evaluation at those points. And for this second row, to construct this second row, you have to use a calculator, otherwise you won't be able to see those numbers or get those numbers with the decimal places. But for the last row, you don't even need a calculator, because all you're doing is looking at 1 plus the point that you consider. For example, for this point here, 1 plus negative 0.5 is going to take you to 0.5. 1 plus negative 0.1 is going to take you to 0.9. As you see that you don't need a calculator to evaluate y at the given sample points. That's the strength of the tangent line approximation, as you see. And then take your time, please pause the video and fill out the table by yourself, and please verify that you got all the points correct. And now the catch is, if you are very close to 0, the function values do not differ, right? Do not differ too much. So here you have 0.99, 0.00002, and then you have just 0.99. That's a very good approximation. And the same thing is happening here, right? 1.99998 versus 1.01. You just rounded it off almost, right? So 1.01 is a good approximation of that number. Here, you still have a good approximation, 1.0998 versus 1.1. That is pretty close, and same is happening here as well. And if you start getting away from 0, if you just consider, let's say, 0.5 or negative 0.5, so we still have a good approximation, but not as good as those guys here, right? So, and then here you have 1.5 versus 1.479. That's an okay approximation, but not the best. So this tells us that if you start getting away from 0, if you just diverge away from 0 much, then obviously the approximation is not going to be as good. So I want to show this on the graph of these two functions. Here we go. So we have the graph of 1 plus sine x, which is the red one, and then we have the tangent line approximation at 0, which is y equals 1 plus x, the blue graph. And you can see that when you are around 0, you can't really distinguish two graphs, right? So, which essentially tells us that a tangent line approximation is pretty strong. If you are around 0, very close to 0, as you see again, that you won't be able to distinguish one from another. Okay, see, I can just zoom in, and then you can't just tell me which one is red, which one is blue, especially here, right? So you can't say that. So, but when I start diverging away from the graph, then the tangent line approximation is not going to be as good. Here we go. So when you go in this direction or in the other direction, as you see that the difference between the red graph and the blue graph is increasing, that means that you're making an error. If you would like to approximate the red graph, the values on the red graph, by the values on the blue graph. And the same thing happens when you go to the other direction. See, like as you go even more, like if you consider like 0.2, let's say, the difference is huge, as you see, between the function values and the approximation. So in other words, tangent line approximation is awesome if you are close, if you're considering the points close to where you have the approximation for. If I change the point, as you see, to another point, tangent line is going to change, that we know from our experience, right? Tangent line is changing here, as you see, and the approximation is going to be different. So if you look for an approximation at 0.2, so why don't you look at the approximation, tangent line approximation at 0.2, and whatever the point you want to consider, just you can sort of like use the tangent line approximation to estimate those values. So here the catch is again that the tangent line changes from one point to another, and tangent line approximation is awesome in terms of approximating function values around the point where you had approximation for. All right, this ends the discussion for the first learning objective. In the next video, I'm going to talk about the second learning objective together with the fourth learning objective. I'll see you there. Bye.